As an engineer in RIISA, Permasilica Group's brand in Croatia, one of my roles is to provide calculation and testing information for the bomb blast-resistant facades that we design and manufacture. Providing calculation and test information is an extremely challenging task from an engineering point of view, as all of our products are all bespoke and there are many factors that have an influence on the overall result. A person could argue, what are the reasons to have a facade which is bomb blast rated? Or how often is bomb blast facade required and a reasonable requirement for a new development? There are many reasons why a bomb blast requirement is needed for facade elements. A large number of important public developments have a need to have the highest rank of safety requirements, as the explosions can be caused by a terrorist attack or a military action. On the other hand, an in-house gas leak, an office building close to the industrial production plant where various chemicals are being produced, or even a sawmill has a risk of accidental explosion. It is important to note that main threat in the explosion is caused by an air shock wave. Only with smaller explosive charges, the small fragments with high speed pose a higher threat than an air shock wave. An explosion is measured with an explosive energy per mass, either a gram when we talk about TNT, or megatons if we talk about fusion nuclear bomb. Before we focus on the facade, it is important to understand what is happening with the pressures when the explosive detonates. The graph shows how the air pressure changes following an explosion. Just after the detonation, the charge creates a spherical shock wave which is circularly expanding away from the explosion. At the head of the shock wave, there is a sudden change of pressure, density, speed, and energy in the air. Shock wave characteristics are the peak pressure and the impulse, which can be measured as an area under the yellow curved line shown on the graph. After the shock wave has passed, we enter the negative phase, which is very important as it has a long effect with a low peak pressure. Now that we covered all the basics, we can get to business. To construct a facade that would resist explosion is considered economically unviable. However, there are three main requirements that a facade needs to satisfy. Protect the people from injury and the main structure from damage, prevent the penetration of pressure into the building due to the explosion, and not to generate fragments or shards that become missiles. From the last two requirements, two things are clear. Facade's frame and infill should be made from a strong and ductile material. For the frame it is relatively easy, as aluminum or steel, the most common facade frame material, fits the description perfectly. For the infill, it becomes a bit more challenging. As we all know, glass is a brittle material, which is basically the complete opposite of what we need for a bomb blast rated facade. But with the addition of a PVB interlayer and creating a laminated glass, we arrive to a solution that fits the requirement. The principle with laminated glass is simple. During the explosion, it is considered that all glass elements will break into small pieces. But due to the flexible and ductile PVB interlayer, the small broken glass pieces stay in place and prevent any shard to become a missile. Despite numerous analytic methods, the testing is still the most reliable method for the assessment of the design. There are two methods that can be used for the facade testing: shock tube testing and range testing. Comparing the two test methods, both of them have pros and cons. Shock tube testing is a more cost-effective test and practical, but although the positive shock phase is acceptable, it is completely lacking the negative shock phase. On the other hand, the range testing is expensive and requires a lot of safety space and safety measures. It is the most realistic type of testing, basically perfectly simulating the real-life condition. Now it is time to show a real-life example of range testing. A project requirement was to design a facade with a bomb blast resistance to the explosive charge of 200 kilograms TNT at a standoff distance of 40 meters from the building, simulating a car bomb in a street. The test was carried out on a sample which was made as a double-glazed unit, 1.5 by 3.1 meters wide, in a size with an external monolithic pane and internal laminated pane with a PVB interlayer. The sample is fixed to a steel chamber surrounded by a concrete block. Inside the chamber, you can see a witness board which is made from polystyrol foam with an aluminum foil. On the opposite side to the charge, there is a concrete block wall where external pressures are measured. Pressure is also measured inside the chamber and in the field. The entire test is filmed with a high-speed and normal-speed camera from multiple positions. After everything has been positioned correctly and double-checked, the test is performed. The next footage will show what was filmed by a normal speed camera. Did you see the pressure buildup at the head of the shockwave? No? Don't worry, there is a high-speed camera footage as well. Look in front of the sample how the raindrops are accumulating. That represents the pressure buildup, and as the shockwave reaches the sample, it reacts, or should I say, it deforms. After the test, the sample was inspected. The external pane was disintegrated, but it was designed as a sacrificial pane. Therefore, it was expected. An internal laminated pane was broken but not penetrated, not through the foil nor through the profile. Therefore, the test was declared as successful. We hope this video provided you with a deeper understanding of the complexities behind designing and testing bomb blast-resistant facades. Ensuring safety in the face of explosive events requires a thorough understanding of both materials and the physics of explosions. From the engineering challenges to the testing methods, we've explored many considerations that go into creating facades capable of withstanding extreme conditions, demonstrating that with the right materials and testings, this facade can endure significant explosive forces.